idea that 3I Atlas could show up in X-rays sounds absurd at first. X-rays feel like the domain of black holes, neutron stars, exploding supernovae, and violent cosmic events. A small, cold object drifting through the solar system should have nothing to do with that part of the spectrum. And yet, when astronomers talk about detecting X-rays from objects like this, they are not joking, exaggerating, or chasing headlines. They are describing a real, well-understood physical process that just happens to sound insane if you've never encountered it before. The key to understanding why 3I Atlas can appear in X-rays is realizing that the object itself is not glowing like an X-ray lamp. It is not hot. It is not radioactive. It is not producing high-energy radiation internally. Instead, it acts like a trigger, a catalyst, something that turns invisible solar activity into visible high-energy light. Our sun does not just shine. It constantly emits a stream of charged particles called the solar wind. This wind is made mostly of protons and electrons, but mixed into it are heavier ions, atoms stripped of many of their electrons. These ions are energetic, fast, and electrically charged, and they race outward through the solar system at hundreds of kilometers per second. Most of the time, they pass through empty space and nothing dramatic happens. But when the solar wind encounters neutral gas, things change. If 3I Atlas releases even a thin cloud of neutral atoms around itself, the solar wind slams directly into that cloud. When a highly charged ion collides with a neutral atom, it can steal an electron in a process known as charge exchange. That electron does not settle quietly. It drops into a lower energy state and releases the excess energy as a photon. And that photon often lands in the X-ray part of the spectrum. This means the X-rays are not coming from the object's surface. They are coming from a glowing halo of interaction around it. A ghostly, invisible collision zone where solar wind ions and neutral atoms meet. This phenomenon has already been observed with comets. In fact, some of the first unexpected X-ray sources discovered in the solar system were comets, and it completely surprised astronomers at the time. These were cold, icy bodies suddenly lighting up X-ray detectors, not because they were energetic, but because they were plowing through a charged environment at high speed. 3I Atlas fits into this framework in a fascinating way. As an interstellar object, it may carry volatile compounds that differ from typical solar system comets. Even extremely weak outgassing, far too faint to produce a visible coma, can still supply enough neutral atoms to trigger charge exchange. Hydrogen, oxygen, carbon, and nitrogen are all capable of producing X-ray emissions through this mechanism. What makes this especially interesting is that X-rays can reveal activity that optical telescopes miss. An object can look completely inert in visible light and still be active enough to glow faintly in X-rays. This allows astronomers to detect outgassing rates that would otherwise go unnoticed. In other words, X-rays can act like a smoke detector for subtle activity. Another reason 3I Atlas stands out is its speed. Interstellar objects move faster than most comets bound to the Sun. That higher relative velocity increases the rate of solar wind interactions. Faster collisions mean more energetic encounters and more opportunities for charge exchange. Even a small amount of gas can produce a measurable signal if the geometry is right. Distance also matters. X-ray visibility depends heavily on where the object is relative to both the Sun and the observer. If 3I Atlas passes through a region where the solar wind is dense or particularly energetic, its X-ray brightness can spike briefly. These bursts are transient, unpredictable, and easy to miss unless you are looking at exactly the right time. This is why space-based X-ray observatories are so important. Earth's atmosphere blocks X-rays almost completely. Ground-based telescopes cannot see them at all. Instruments like Chandra and XMM Newton orbit above the atmosphere and can detect extremely faint X-ray sources. They are sensitive enough to spot subtle emission halos that would be invisible in any other wavelength. When astronomers point these observatories at 3I Atlas, they are not expecting a bright beacon. They are looking for a faint excess of X-ray photons, just above background levels, concentrated around the object's position. Detecting that signal requires careful filtering, long exposure times, and precise modeling of background noise. If X-rays are detected, the implications are significant. It would confirm that 3I Atlas is interacting with the solar wind in a measurable way. It would strongly suggest the presence of neutral gas around the object, even if that gas is sparse. That, in turn, provides clues about its composition and thermal history. If X-rays are not detected, that result is just as important. A non-detection places strict limits on how much gas the object can be releasing. It would imply a very dry surface, possibly stripped of volatiles during its long journey through interstellar space. That would tell us something profound about survival in the void between stars. There is another layer to this story that makes X-rays especially valuable. Different elements produce X-rays at different characteristic energies. By analyzing the energy distribution of detected X-rays, astronomers can infer which atoms are involved in the charge exchange process. Oxygen ions produce different signatures than carbon or nitrogen. This turns X-ray detection into a kind of chemical probe. For an interstellar object, that chemical information is priceless. It offers a glimpse into the makeup of material formed around another star. It allows scientists to compare that material directly to what we see in our own solar system. Are other planetary systems chemically similar to ours, or fundamentally different? X-rays help answer that question in ways visible light cannot. It is also important to clear up a common misconception. X-ray emission does not mean danger. It does not mean radiation blasting through space toward Earth. The emissions involved here are extremely faint and localized. They pose no risk. They are simply photons released during microscopic interactions, scattered harmlessly into space. The reason this topic feels shocking is because our intuition about X-rays is shaped by extreme environments. We associate them with violence and heat. In reality, X-rays can be produced gently, quietly, almost accidentally, as a side effect of charged particles brushing past neutral atoms. In the case of 3I Atlas, the object becomes visible in X-rays not because it is powerful, but because space itself is active. The solar wind is constantly reshaping the environment around every object it encounters. Most of the time, there is nothing for it to interact with. When there is, even briefly, the interaction lights up. This also explains why X-ray emission from such objects can be intermittent. As the solar wind fluctuates, the signal can appear and disappear. A detection one day does not guarantee a detection the next. This variability is not noise. It is information. It reflects real changes in solar conditions and the object's interaction with them. For astronomers, this makes X-ray observation both frustrating and thrilling. You are chasing a faint, fleeting signal from an object that will never return. Miss it, and the opportunity is gone forever. Catch it, and you gain a data point that may not be replicated for decades. There is something poetic about this.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.